skip the chit chat and let's introduce here Igor. Welcome, Igor, to the stage.
Okay, thank you. It's in the film, Igor. I'm Igor. Yeah. Okay, no problem. Okay. Thanks for very kind introduction, and thanks for this very nice meetup. And yeah, I'm really grateful to the organizers and how everything was managed. Okay, we 2 years ago we started developing this technology that makes available checkout less the exit in the supermarket. The short, let's say, pitch of this startup is a Amazon Go alternative. Okay. Okay. I will introduce you a team. We have a team of mathematicians, AI engineers, so physicists, statisticians. I'm an applied mathematician, and we are working on this project for 2 years. And I just cut out the main machine learning stuff from our project, but you have to understand that it's only maybe 30% of the project. Okay, so automated checkout, what a beast. Okay, we formulated as three main machine learning problems. It's actually, obviously, it's a minimal viable, so you have to always like do a lot of glue machine learning to glue them all together. Okay, so the first problem is the pause estimation and people tracking. It's let's say there are different approaches for the checkout, but let's say it's become already ubiquitous because we are not alone. There are approximately about 10 startups already working for more than a year on that in the world, and few of them are really big. Okay, to call some standard cognition, zipping, they collect a whole bunch of money. Okay, to do that. We talk with them. We not work with them, but we exchange ideas. And actually, it is strange. We have to be competitors, but we exchange ideas. Okay, because the problem is hard. And okay, so first is pause estimation and people tracking. The second is object tracking, and we treated this iteration as mostly as anomaly detection. It was quite sufficient to treat the exchange of the products on the shelves. Okay, and then you have to fuse all these together. So it's you have to solve an assignment problem. So who did what? Who picked what from the shelf? Okay, but first you have to build physical system that actually produces data. Okay, so and we came with let's say maybe a few years ago it was not common. Now it's quite ubiquitous, is to place the scales on the shelves. Okay, so we tried to find any scale productions. I contact them when I explain our needs. Like they tell me, "You're crazy. You don't need that." No, I told we need that exactly. We need it because it's a scale, but it's not a scale. Okay, it's actually a sensor that produces a raw output, and we analyze it and we classify. It solves quite a lot of issues, but it still introduces a lot of issues. Okay, so it's a physical device, so a physical world is hard. Okay, so it counts the amount of products. It gives us approximate place where the action happened. So what else? we didn't try it, but probably we even can classify different products you place on the scale from the signal of the response. Obviously, the typical example of water with respect to the something salty, something rigid. Okay, so I will show you. That's actually so we developed from scratch the scale. So we kind of reinvent the wheel, not completely, but partially. Okay, so the scale produces these signals. It's 50 hertz. So first graph is the peak action when you simply raise the product from the scale. The second one, you drop the product on the scale, and it is exactly the Coca-Cola can. You see the dumping happening, typical dumping graph. Okay. So we developed with one of our partner here in Milan the firmware and the logic. The logic is quite simple. It's mostly all the time in idle state, so it sends no signal. And when it feels any action it's very sensible. It's enough like to touch it like that, and it comes out of idle. And it sends, produces these type of outputs. Okay, and then another beast. So you come to the client, you say, okay, we do automatic checkout, and they show you a place where you wanna they wanna build it, and what they give you this. And you cannot visit that place usually. Okay, so it's a 2D drawing. They say you at least the ceiling. Okay, it's 3 meters half high, and then also they say you can mount cameras here, there, and here. That's it. Okay, so it's very challenging, and from also the point of view of the computer vision. And yeah, we did the whole pipeline, and the guy who did that present here in a room, so you can ask how it works. Okay, so first we build the 3D module, then we start the make intersection of the cameras. So for our algorithms, we need like every point of the space should be visible by 2 cameras at least. We use 2D cameras, so no depth. Okay. Then we build this kind of 3D body. We analyze it. We like this. We don't like their blind spots. Is it okay for us or it's not? Okay. And then the current evolution of the algorithm is just to why not to use machine learning just to find the best disposition of the cameras inside the space. So we load the 3D module and we run that's one particle optimization, but it's similar to genetic algorithm. Okay, it's quite heavy, but in one night you obtain some nice disposition of the cameras. Okay. We're working on introducing that constraints of the client. So you have to place here a camera and there and so on. Okay. Then, yeah, pose estimation is also, I'm not an expert, but the expert is present in this room. You can talk to him. So I don't hide being inspired by OpenPose module, but the open source is not usable for this purpose. We rewrote it from scratch. I don't know who put a hand on the OpenPose module here. No one. Okay, it's an ensemble module that consists of the layers of CNN. It's a VGG or ResNet on your preference, pre-trained on ImageNet. Okay, so this is a first part neural network that produces heat maps. So it's a kind of a grayscale output. Okay, so 2 types of heat maps is for joints and limbs. Okay, then there is another sub module of this ensemble that takes it and produces, makes a reduction of the heat maps to the peaks and the limbs, exact limbs. Okay, so it becomes 0 and 1-dimensional objects. Before it was like a 2-dimensional distribution. Okay, then there is another algorithm which we couldn't implement on TensorFlow, but we're working on that in GPU. That makes this assembling of the skeleton, and then it produces the final skeletons. Okay, so you can see on top the final skeletons. Okay, so we train. How much time I have? 10 minutes. Okay. Okay, we train our pose estimator on top view dataset, so it helps a lot. Not yet done yet, but we're working on that. Then our cameras and all system is synchronized in time, so it's very important for the multi-view and so on. And we're working on a reduction of CPU and put everything in GPU. Okay, on top of that, so we pose estimator produces these 2D poses, 2D skeletons. Okay, so you have to first to go finally in space, so make a 3D skeletons and then track them. So we have to match 2D pose detections in different cameras and produce the 3D tracks. Okay, so it's a typical view of 4 cameras of the same scene. If you can see, the cameras are not perfectly synchronized, so they are not like triggered with milliseconds, but it's sufficient enough because the human time is quite slow. So if you work up to 10 to 30 milliseconds, it's almost the same. Okay, some glossary. Okay, for the detection, we, as I told you, is just 2D pose of the skeletons. Then reconstruction already lives in 3D space, so it's actually from different frames. So from the frame 1, detection 1 is connected to the frame or to detection 2 in the frame 2 or something like that. So it's a reconstruction. Okay, and then the track is the reconstruction maintained in time. Okay. We implemented this article for hypergraphs for joint multi-view reconstruction and multi-object tracking. It treats in probabilistic way the tracks. And all the scene, also reconstruction, it treats in a probabilistic way. Every point of graph has its own, is associated its own probability. If you read an article, it's very good question how you how you associate probability to reconstruction, okay, or how you to the joints and so on and so forth. So what we do, as I told you here before, we have to pass from detections to tracks. Okay, so what is detection is every single point. So 1, 2 is already reconstruction. Okay, so this one and so on. I'm also not an expert of that, so the person who is expert of that is not present here. Okay. Okay. Associate probability. Okay, we associate probabilities to every reconstruction and every link. We create that hypergraph, then you have to convert it and redefine it as a binary integer programming problem. Then you pass it to the solver and it returns you the track. And the track is the exact connection of this reconstruction. This is an error of time, okay? So it's returns you those tracks. It's an offline algorithm, so we have to risk quite a lot when we started implementing it. It took us 6 months to implement that. And we knew that it's offline, and we made a window approach to make it, to glue tracks from one to the other. And it's quite unstable on the glue, and we developed another now approach to treat it also as a BIP problem with a probability so now it's become stable. And after all, the tracking is quite stable, and we are really satisfied how 3D tracking with the skeleton works. Okay, so the bad part is the good part is no ID switches. The bad part is quite computationally expensive, and the ugly part is in NP hard. Okay. Then we feed that geometry, because the camera 1 will never actually, you have to triangulate with camera 10 because it's from the another room, another 3D space. So we introduced that, and it reduced a lot the computational complexity. Okay, so we feed those 3 frames. We call our magic, and what happens? It doesn't work. You see, the limp of one person is associated with the other, and so on. Why it's so? Because it's very sensible to the geometry. So you actually have to calibrate all probabilities, because the algorithm takes into account also false positive, false negative rate of the module itself, and a lot of parameters. So in every step, we have a calibration procedure for all algorithms, and after you calibrate it well, you obtain a good tracking. Okay, object tracking and anomaly detection. Yeah, it's quite clear. The misplaced products on a shelf. Different approaches. Also, you can talk to the person who did that tonight. Okay, 2 of them actually. Okay, so first is out of distribution. Then we tried out encoder, and then regular object tracking. And after all, which we did another that actually feed the reference image, so it's a correct image of every section. So we have this kind of a planogram of the shelf, no? So we bisect all the racks, and then the actual image, what is happening now, and we train two ResNets, 2 networks that share weights, and to discriminate whether it's anomaly or not anomaly. Okay. Hot dog, not hot dog. Okay. Let me show you how it works. Okay, there are different snapshots. When it's green, everything is okay. Okay, when it's red, oh, oops, sorry. Oh my God. Okay. So it's examples from the let's say dataset when it's the shelf is not anomaly, and when it's anomaly. Here I wanted to show. Oh no, I couldn't. Okay. Sorry. I wanted to show we also introduced the occlusion. As you see, the person was in front of the shelves, so the model also predicts when the different parts of the rack. Oh, okay, I couldn't. Okay, you have seen when the different parts of the shelf is occluded, so it predicts, gives the score. Okay, so not to obviously make a decision when it's occluded. Okay. And then the final problem is the assignment. So we treat it also in probabilistic approach. The event is composed of the timestamp of the action. We have a peak and drop action. Then the scale when it come from, which scale it come from, then the product ID, the quantity, and the user associated, okay, to it. So everything of this is fitted to Data Fusion, and it predicts the cart. Okay, we measure this with we create the ground truth. So we calculate as simple intersections, so set intersection between predictions and the ground truth. So we calculate all these standard measures. Okay, all on the cards. And then we also made a module that watches trajectories of the hand in front of every shelf, and we feed these trajectories to the module, and it predicts whether it was a real action, okay, or it's not. So we actually did very strange like peaks like that, just to make it as more variable as is possible. Okay. Okay, there's still a lot to do. Like I can tell you some secret. If you hit with the leg the product, and then you pick it from the ground, and then you throw it, you can maybe steal from our store. Okay, dataset for automated store. Yeah, we made the. I tried to find an annotation tool for our needs, but I couldn't. I spoke with a lot of people. Yeah, we decided to do it. So we needed a multi-view, synchronized frames, and we needed for tracking. So we did this annotation tool with one company, we start using it quite soon. Okay, so you see it's a simple annotation in a COCO format that returns the skeletons. Okay, we also did a synthetic 3D store rendering just to try different views from top view, because it's actually we couldn't find the top view camera annotation for pose estimator. It doesn't exist. Maybe we will do sooner or later. Okay, so that's Unity 3D rendering with the random products on the shelves and so on. The people are moving. They do some. There is a grab action we programmed. So and the module actually predicts. It actually works. And you feed it with these images, it becomes more robust. Okay, the architecture. This is very simplified architecture of ours. Okay, so we have a set of camera scales that produce raw data, and we have the services we call video capture that makes 2D prediction, so pose estimation, and video manager that collects all of this and produces tracks, so in 3D, triangulation in 3D. Then Data Fusion is the guy that fuses all the information and solves the assignment problem. And then there is the dashboard, visualization, backend solving stuff, managing carts, and all this stuff. Okay. And that's, let's say, front end and back end. So we have this fancy visualization, which is a 3D. Is actually, you can rotate, you can see the shelves, how it's actually disposed, and it's all dynamic. So you place one product and, okay, quite fancy. Actually, that one sells very good with the investor. When you show it, like, wow, that's intelligence. Okay. Okay. And the cart. That's actually what we are combating for. So you arrive at the checkout, and the system says I have a Coca-Cola and original in your hand. That's the holy grail of our. Okay. That's it. Thanks.
Thank you, Igor, for the talk. So if you have some questions, we are happy to have it for like 5 minutes maybe. Yeah. Anyone have questions? Okay.
Yeah.
Wait, because we are recording.
I've seen that you use a faster RCNN. Did you consider YOLO? YOLO is
yes, we consider all the architectures. Yeah. Okay. Actually, as I told you, the one implemented is the, let's say, this architecture. It's not faster CNN. Okay. Yeah, we tested obviously YOLO and all the stuff. Yeah.
Do you have a target speed that you want to achieve in the recognition?
Yeah, it depends for which task, but as we saw, because of the human time, so 10 FPS is absolutely 10 FPS, yes. You have to be really fast to trick our system like that. That's very fast, no? Yeah, 10 FPS is very fast, but now, right now we work, it's fine 5 FPS for now, yeah. If you are a legitimate customer, so if you pick like that, 5 FPS is enough, okay, to detect the peak.
Also, have you considered the other way to track, like yes, using beacons? Some sort of beacons or NFC?
Yeah, yeah, we consider, we discard it because of like, you have to ask every customer, okay, pick that, I will track you. No customer will come to your supermarket. Okay.
No, I was thinking tagging the content.
Tagging the content, yeah.
That can be done.
Yeah, to attach yeah, to create a data set, yeah.
NFC, you know,
yeah.
A powered NFC, you've got 2 meters.
Absolutely, absolutely, yeah. We don't have much experience with that, but I thought about that. You okay? Nice to meet you. Okay, good.
If I understand well, you ended up treating this problem as a
who's speaking?
Me.
Okay, sorry.
As a face recognition problem.
Face? No.
Are these two faces the same person or not? It reminds me
okay,
of...
it's a face. It's not the face. Is a
no, okay, but I mean the architecture is typical for face recognition. Is these two the same person?
It's a general architecture.
I wonder how did you train this? What kind of laws? You know, triple laws.
I don't know.
Don't know. Okay.
Question.
About the dataset generation.
Actually, this is an appetizer talk, okay? And now you have to call all our engineers and we will talk what laws we were using. I'm not hiding. I really don't know.
About the dataset generation for the pose detection.
Yes.
You choose to make this annotation, which looks to be a huge work. And
yes.
Have you considered to generate it automatically with some sensors for people? And why you discarded that?
No, we didn't discard that.
Okay.
We had no time and resources to implement that. Okay.
So, but you had time to annotate.
But actually, our system is a system that produces data. It's most of the time is correct, but there are some let's say anomalies that you can detect in their predictions, and that they give a hint what actually is a hard cases for we actually know the hard cases. Just you need to let's say people, very close people, the pose estimator goes crazy. Okay, it doesn't know whose that hand is and so on. Okay, so yeah, absolutely, yeah, sensors and triangulation through the system of NFC or even visual tags. Like it's enough like green, and then you can do it with computer vision. Okay.
Any more questions from this side, or I don't know? Yeah, wonder.
We even made a joke like when you enter a supermarket, there is a robotic hand that puts a hat on your head with the Aruko code on top, and that's all too much.
Are you already managing cases where a family uses the same basket but different people?
Yes. No, not yet, but we plan. It's actually matter of the group on the software level. Okay, we treat every person as identity, as a person. Okay, so it's matter to group them all. That's a software task. That's easy.
We have time for one last question, if anyone has, or
yeah.
Is there some? Okay. Okay, so maybe we can have like afterwards. Thanks a lot, Igor, for all your explanation.